Adiabatic change. You think of one? Anybody think of one? Has to be something that what is or isn't happening. What does it have to be? Adiabatic. What is it, Amberly? What is it? Okay, there's no energy leaving. What type of energy, though? That's what makes it adiabatic. What type of energy? Heat. Now, leaving what? The system. All right, there's no heat leaving the system. What would be an example of one, though? Okay, well, water can be your system, but yeah, keep going.
Wouldn't that be like your thermos kind of thing that you were doing the other day?
You could have a water in a styrofoam cup or something, right? But nothing's really happening, right? You just have water in a styrofoam cup. Well, what could you have in the water in the styrofoam cup? You could have some ice. Well, that's a good one, right? Okay, have some ice. Is an adiabatic, the styrofoam, right? Is it going to prevent the ice from melting? Now, that if it's truly adiabatic, that heat can't get transferred to the surroundings, that ice is still going to melt? Within the system, yeah. How? The water. The water's at a higher the water's in a lower energy state, right? Or higher energy state, however you want to think of it. The energy can get transferred from where to where? The ice to the water, or the water to the ice? Water to the ice. The water's a lot hotter, right? Okay. There's another example of an adiabatic process, and that's my voice. What's sound? Yeah, I know that, but what is sound? Waves. Waves of what? Yeah, energy. But, yeah, energy in what form? How is this energy being transmitted from? Vibrations, we're getting there. In what?
In the air.
In the air. Okay, now these vibrations in the air, what are they? Yeah, air's made of molecules. But what is sound? We're getting there.
Oh, the crashing of the molecule, isn't it? That's causing the sound.
Yeah, you're getting there. You have regions of high pressure and low pressure, right? Compressions and rarefactions of air. Going from here, hitting your lobes. What is it? Isn't that lobes or something? Anyway, you biology people. Okay, how about this? Is all this hot, smelly air from here actually hitting your lobes, Emily? Right? Is my air, because you're talking about energy and energy being transmitted, is it actually hitting your ears? The air molecules that are actually in here, are they hitting that? Hope not. It'd be pretty slimy and stuff if it did. No. So how is that sound getting from myself to your ears? What? It's bouncing. It's compressions, rarefactions of air. It's energy, mechanical energy being transmitted from here to there. The air's not going from here to there. It's just, right? You can't feel it unless you're super sensitive. You could feel that, right? Compressions and rarefactions, right? Rarefaction, less pressure, low pressure. Okay, so what I'm trying to get at is sound is supposed to be adiabatic. These compressions and rarefactions of air are happening so fast, and there's such a small amount of space there that there's no time for heat to diffuse. But how could you make that space that be really, really small in the sound? Would that be a really high frequency or really low frequency? High frequency. So if you want this to be non-adiabatic, you have the pressure really high and really compressed over a very small range. Now that's really high pressure, very small range, heat's going to diffuse. What's the consequence? Well, the consequence is someone outside with a horn. Would you want that to be a really high pitch or a really low pitch for everyone to hear this? Really low, because high pitch is that energy is going to dissipate, right? So you'd want it to be a low frequency, but then you got to take into consideration everyone's sound sensitivity, the human hearing. I'm sure all frequencies aren't the same, right? So you want to take that into account too. But okay, so adiabatic changes that are around you. Just kind of you have to look kind of hard. So if we have a adiabatic change, oh, here's some equations. I don't think they're even written down in here. I should add them. Well, that gives us something to write, I guess. Delta H equals CP delta T. Okay. Or you could have delta H equals CPM delta T, but something's missing. Now first, let's go back to delta H equals CP delta T. Enthalpy is the change in temperature times, what's CP? Yeah, the subscript P means constant pressure. Heat capacity at constant pressure. Right. Okay. So the exact same equation, and heat capacity is just joules per Kelvin or something. CPM, and the next one, Madison, where something's missing. What's CPM? CPM, what's that? Yeah, just per mole. Molar heat capacity at constant pressure. Okay. So those two equations, you want them to be the same. You want to end up in enthalpy, joules. What's missing in the second one? We have a molar heat capacity, number of moles. What's our symbol for number of moles? Little n. That's what's missing, little n. So we have a couple equations. Now what's interesting and what helps with our homework is, here's an equation. I call it a definition, a law. Does that always hold?
Yes.
Kathleen, does that always hold? It's a reversible process. It's an irreversible process. It's constant volume. It's an isotherm. It doesn't matter. It always holds. Right? How is enthalpy defined? Amberly, do you remember? So this, in other words, delta U Q plus W always works. Right? Safe bet. Always. Amberly, how is enthalpy defined? What was it? Well, it can be part of internal energy because delta U is delta H plus PV and stuff. But it was the heat transfer. But what had to be constant? Pressure. That's how enthalpy is defined. So it doesn't matter what process you have. I mean, you can always find enthalpy. Sometimes it'll be zero, sometimes it won't. But you can't change the definition of enthalpy. It's the heat transferred under constant pressure. So that means this also is a definition. This is how we define enthalpy. So it always works. They may say, oh, the pressure in the problem, you know the pressure's changing. You know the volume's changing. It doesn't really matter. It's a definition. It's how enthalpy is defined. So it sounds weird to calculate enthalpy for a process where pressure isn't constant, but it's a theoretical idea. But that's how, just so you remember that enthalpy equals molar heat capacity times the number of moles times change of temperature. That's how enthalpy is defined. So whether the pressure's changing or not, you can use that. Okay. If, Sandy, we're going to have a gas in some container. Yeah. And this lid is really nice and loose. And then there's, I don't know how you do this. You'd have to have a vacuum or something up here so that this lid can come up on its own, right? But nothing can go inside the system, so little end doesn't change. So that this little lid is loose, and it's an adiabatic expansion. This lid goes up, so the system's doing work on the surroundings, expanding it. What would happen to the temperature of that gas inside? Would it change? This adiabatic process. And he's doing work on the surroundings. But it has to be adiabatic, right? That no heat can get sucked in, or no heat can go out, or no heat can be transferred. Would the temperature change? What do you think? She says temperature stays constant. Everybody agree? If you say temperature stays constant, there's a problem.
Because you're expanding, so you have
You're expanding, so you have more space, but the key point, the key statement, which is kind of hard to catch, is that this guy, he did what on the surroundings, this system? He did work, expansion work. And we have a couple equations to calculate it. Depends on whether it's reversible or irreversible, right? But the point is he did work. If the temperature doesn't change, where else did the system get the energy from to do that work? The temperature in this gas has to go what? Has to go down, has to drop like a rock. Because that's the only place he can suck up energy is himself, the molecules themselves. You can't suck it from outside, like an engine or something. No, man, so his temperature is going to drop. Okay. So that's, now if it's a reversible and it's an adiabatic change, there's some relationships here. You see the little gamma. Okay. Probably the little i's and the little f's probably mean what, Anna? In that relationship, what do you think the little i's and the little f's mean? Yeah, initial and final. Okay. So we're used to seeing that P1 V1 equals P2 V2 if you keep the temperature constant. Well, not for adiabatic. Right? It's not quite that straightforward. Right? It's close. P1 V1 equals P2 V2, but you have to raise the volumes to gamma. Okay. And only if it's reversible. Do it nice and slow. You get this. Okay. And same thing with the temperature, volume-temperature relations. Okay. But now little c is defined as the molar heat capacity at constant volume. Okay. Well, I wanted to try something here, I think. Oh, that's down here, Montan perfect gas. Let's not play around with it yet. For work for an adiabatic, reversible or irreversible, W is minus NCVM delta T. Okay, so now we have another equation for work, but that's obviously not a definition like internal energy is heat plus work. It has to be an adiabatic process to calculate work that way. All right. Let's see. If we played with this a little bit, play with this enthalpy equation a little bit. For example, if I put a delta in front of the H, right, change, where do I put the changes on this side? In front of the U and in front of the PV. Well, yeah, we'll be playing out. You're right. We can put it in front of the. Okay. And all I want to do is play around with it. Let's say the pressure is constant. That's the first thing we can play around with. Pressure's constant. How would this change the equation? Delta H would now be delta U plus P delta V is the game we're playing, right? P is constant, so you pull it out, and then you get P delta V. All right? You could say the volume's constant. Right? Then what relationship could you write? Delta H equals, yeah, V. Delta V. Delta P. We could play around with it where we had, go back to the beginning, delta U plus delta PV. If it's an ideal gas, what does PV equal? nRT. So you could say delta H equals delta U plus delta nRT. Now who cares about pressure and volume, right? The question may not give you anything about it, but you can monitor enthalpy this way. Usually what changes? T, right? N and R, everything's usually sealed, closed systems. So there's several relationships here. There's one, there's another one, there's another one. And if you look at the equation sheet, this is the only one I give you. Right? So being able just to mess with the enthalpy and realizing what's changing, what's not changing. Just kind of go after what you need. But it all starts with this one definition. Okay? Let's check out for a monatomic perfect gas. Let's erase some stuff here. Right here. For a monatomic perfect gas. What's a monatomic perfect gas? Juan, what would be an example of a monatomic perfect gas? What would be the identity, an example of something like that? Whether it's acting perfect or not, I don't know, but what could be an example? Monatomic. Yeah, same throughout, but yeah, otherwise there'd be more than one in there. Well, no, what would be an identity, an example of one? I guess what I'm driving at is what's monatomic? One atom. So is there such a gas? Look at that. Hydrogen is H2. Nitrogen is N2. Are there any gases that are monatomic? There's a hint. If you look up there, you'll see them. The nobles, right? Definitely. Neon, argon, krypton, xenon, radon. Those guys are all monatomic. So if they're going to have some homework questions on it, I bet you that's the gas that they're going to be messing with. And all I want to do is help you out here and get a value for gamma for these guys. So they may not say monatomic perfect gas, but if you see it's argon, it's monatomic. They may not be so obvious. So gamma is CPm over CVm. Now the denominator has to be 3/2 R. Right? Because what I'm doing is I'm substituting into this. Just to play around with this. Right? What's my gamma for a monatomic perfect gas? Well, the bottom has to be CVm. And for a monatomic perfect gas, it's 3/2 R. Now we had a relationship, I forget what it was. R equals CPm minus CVm, or where's our equation sheet? The gas constant related those two. There it is at the very top. R, we know that R equals heat capacity at constant pressure, that one. minus the molar heat capacity at constant volume. Okay. So we know that CVM is 3/2 R, right? This is supposed to be CPM right here. Well, according to this, R plus CVM, right? See, if I rearrange this one, I just get that bottom one, right? But now we know that CVM is 3/2 R. So what's R plus 3/2 R? 5/2 R. Yeah, because if you don't see it, it's kind of like saying 2/2R plus 3/2 R. Yeah, 5/2 R. Okay. So this is really 5/2 R all over 3/2 R. We end up with gamma being what? You're just left with, can you see it? The R's are going to cancel. You're dividing both top and bottom by 2, so they're going to cancel too. You're just left with 5/3. Okay. It's kind of odd. But you can play the same game. We probably should play it, right? Let's get our gamma for this guy. And then you'll be ready for the homework. A nonlinear perfect gas. Okay, a nonlinear perfect gas. Well, there's a good example. Good question. What's an example of a linear perfect gas? Two dots make a line, so any diatomic is going to be linear, right? Any diatomic could be linear. Just you have to have, I don't know, at least 3 molecules, 3 atoms or something. I'm sure it'll be obvious. It'll be ethane, propane, butane, right? Something that's floppy. Yeah. Okay. So let's get our gamma for a nonlinear perfect gas. So we said our CPM was, what did we say it was? Oh, we have to go up there and, no, we just found it, didn't we? 5/2 R? Yeah, it was R plus CVM. CPM is R. I don't want to screw up, so I'm going to write that in there. Otherwise, I do something in my head here. Right? CPM is R plus CVM. CVM is now 3R. R plus 3R would be 4R. So my gamma is going to be 4R all over 3R. It'll be 4/3. So for a nonlinear perfect gas, my gamma in these relationships will be 4/3. For a monatomic perfect gas, it'll be 5/3. Okay. Alrighty. I think we're ready for the homework. Okay. What's that? Oh. What do we call, we're not used to talking like that. We're used to saying isotherm. We're used to saying,
Isn't that the PV plot thing?
yeah, when you make a plot and you keep temperature constant, we call it an isotherm. If you make a plot and you Now what's the condition? You make a graph, a plot, and you're plotting these parameters. And what can't be happening? You call it an adiabat. No heat exchange between system and surroundings, whatever they're talking about. And then it's an adiabat. Okay. And it's kind of a big deal because that's the only way to make an isotherm is if you suck the heat out, if you added heat. That's how we got isotherms. So adiabats, man, things are going to be getting colder, getting hotter, because you can't allow any of that heat transfer to go on. Okay, some questions. We got a bunch of questions. Now we're giving you something to do. Okay. Now, what are we? A sample of 1 mole of, that's supposed to be H2O? Man, you have the book. Look up 2.8. Is that supposed to be H2 or H2O?
2.8, A or B?
2.8A exercise.
It should be H2O gas.
It is, should be H2O.
H20.
Yeah. Okay, no problemo. We got it. Okay, a sample of 1 mole of water is condensed isothermally and reversibly. Okay. Isothermally and reversibly. And we have 1 mole of water. It's going to liquid water. So it starts out as a gas, I guess, right? At 100 degrees Celsius. Standard enthalpy of vaporization of water is 40.656 kilojoules per mole. Find W, Q, delta U, and delta H. W, Q, delta U, delta H. Okay. Can we start slapping zeros on stuff? It'd be nice, but... Is the internal energy changing? What's a question we usually asked?
It's isothermal.
Isothermal, so we just slap a zero on it, right? Don't write it yet, though, Adriana. Why not? That only works for what? Gases, right? Is this a gas? It starts out as a gas, but it didn't end up as one. So definitely, because think about it. If you want water gas and it's going to condense into a liquid, does that give off heat or does that suck up heat? All right. What helps me is...
Gases are higher energy liquids.
Yeah, that's what helps me. I do my little energy thing here. Right? Energy's going up. We're going from a gas to a liquid. We're dropping down in energy. Man, this thing is going to get hotter or colder. You're going from a gas to a liquid. Right? It's condensing. It's starting out this really high energy. You end up with this thing down here. That heat has to go somewhere. It's lost. This is going to get warmer, right? Okay. It's not like sweating. It's not like sweating. Sweating is where, I'm all sweaty and then it just evaporates. That energy, ends up in a higher energy state. It had to suck up the heat from somewhere, so it sucks it up from your skin and stuff, right? Here, this is why your cans of Coke get hot, sitting out there at the picnic or on the table, right? Okay. Because you have a gas in the atmosphere, and it just condenses. It gives off all this heat, goes to a lower energy state. So anyway, there's heat's been. So you know right now, Q isn't going to be zero either. None of this stuff is going to be zero. Enthalpy, it's all happening under constant pressure. right? There's going to be something for all this. Okay, so let's start with the ones that might seem easier. For me, the easiest one is Q, because I remember this general chemistry stuff that we're doing, and we have this heat capacity stuff. Right? If you ever want to calculate how much energy it takes to warm up this jar of water such degrees, right? Q equals, you look up the heat capacity, multiply times the change in temperature. Okay. But it's not quite that. How can we get our Q? It's a phase change, right? We're going from gas to liquid water. That always works, but we're going to have to find Q and W, though.
Where's W and delta U?
But how can we get that Q on a phase change? The whole idea of isothermal and reversible, don't let it look, it looks ugly up there, but remember, all phase changes are. You can go backwards and forth on them. So they told us enthalpy of vaporization of water, right? If you want to go from liquid to gas or gas to liquid, and you want to calculate that energy, you had to use delta H vap, right? And if you're not sure how to do it, just look at the units. Does temperature even come into play? No. To get the enthalpy of vaporization, and you put a plus or minus on it depending on whether you're going from liquid to gas or gas to liquid, you have to do that yourself. But how would you get that energy? According to the units. Yeah, find the number of moles and multiply it by delta H vap, right? That's all the units are telling you. I don't even think you even need an equation. I'm looking at this guy thinking, all I got to do is multiply by the number of moles, and I'll have the kilojoules. I just won. I made it too easy, right? So it's 40.656. Now, yeah, and that's kilojoules. 40.656 kilojoules. You have to put the plus or minus on there, though. And it's going to be what? You're going from up there to down there. Has to be minus. You're giving off heat, right? It's exothermic. You're giving off heat. So we have to put the minus on ourselves. Okay. So we have the Q done. Oh, we have some equations for W. Man, we have a bunch of them, don't we? We have minus px delta v. We've got minus nRT natural log v final or v initial. Now we've got a new one. NCVM delta t. Which one works? It says isothermal and reversible. Now they didn't say anything. Is this adiabatic? They don't say anything, so I wouldn't mess with adiabatic. Adiabatic is really special. They're going to use the word adiabatic because it's a very special thing. Okay, so not that one. If we did the isothermal reversible one, what would you plug in for V final and V initial? This because V final, it's a what? It's a liquid. So how would you get V initial? V final, there isn't any gas. I mean, it's all condensed. For VI, we could use PV equals nRT. So this one really isn't going to be a problem. But V final, that's what I'm getting at. V final, it's all condensed. It's not even a gas anymore. It's a liquid. So it's really 0. Natural log of 0? What do you get on your calculator? Do you get 1? Do you get 1? You get error, don't you?
Yeah.
All right. So it might come out to be the same. I mean, if you just assume this is 1, but it's error, so I would rather just have you come up here and show you what to do. So, because now it's cleaner. What's delta V? It's what minus what?
Final minus
V final minus V initial. Well, we said V final was 0. So now you just plug in what V initial was. Use the ideal gas law. Or just, right? nRT, V is nRT over P. So if we just, W is minus P external, right? Times our V, our negative VI. And what's VI? It's going to be nRT over P. Do we care? Do we care?
It doesn't change, so no.
Do we care?
Would it be negative still?
Oh, did I lose my negative?
No, it's there.
But see what happens to the P's?
They cancel.
Cancel out. So we're left with nRT. So if we would have done nRT up here, we would have been okay. I think it's a limit question. Whereas as the natural log approaches 0, right? Anything to the 0 power is 1. But it's a limit. I mean, you're not at 0, you're approaching it. So that's the problem with the calculator, I think. But if you don't see it, you just use the macroscopic change. It works out, nRT. So we have W now. And then Rob told us this relationship, so we have delta U. All we're missing is delta H. What are you going to write for delta H? What's that? Oh, we could do that. I think we could do that, couldn't we?
Is that negative P external times negative VI?
Pressures. But I think delta H.
Yeah.
There's a hint. There's a hint to finding delta H. I mean, we can go a complicated way and get it, but enthalpy of vaporization. What did we use to get Q? We used the enthalpy of vaporization. We used enthalpy. We really didn't notice it. We used enthalpy to get Q. Q and enthalpy are the same thing here. Right? They're the same thing. And we should have really wrote our answer for delta H first, because that's what we found. We found the enthalpy of vaporization. We found the enthalpy. At the very beginning, we just didn't really realize it. So your delta H answer is the same as your Q answer. Right? You use enthalpy of vaporization to get it. That make sense? How about something like 210? What are you missing, or what do you need to do to solve something like 210? enthalpy of fusion of, Rob really helped you out on this. Because if it's not in the book, you're going to have to Google it. And those are the exact right terms you're going to have to Google. The enthalpy of fusion of sodium. I don't know where it is, but you find it. And let your units kind of tell you how to mess with it. The units, I'm sure, don't even have Kelvin in there. It melts at the temperature it melts at. Okay. And when you do get your answer, now it's going to be so many joules or kilojoules per mole probably. So convert your kilograms into grams and into moles. So that won't be a problem. But in the very end, this is the part that you have to determine. Do you put a plus or a minus on your Q? If you want an equation, maybe it would look something like this or something, right? Because I'm sure this is in per mole. It's not. I'm sure it's in per mole. Enthalpy is always in per mole, never per gram. They throw in the word specific if it's per gram. So I'm sure it's per mole. Small pi times per mole. Do you put in a plus or a minus? A plus? We're going from metal to liquid. Exactly. We're going up the ladder.
Do you want the delta H for fusion and sodium? Right
Yeah. Then I'll help people out. What'd you get? Where'd you find it first?
Page 928.
Okay, just so that you know, page
Table 2.6.
928, and the number is
0.
enthalpy of fusion of sodium metal.
I can't make that up.
That's not right.
NaS. I swear to God.
Sodium.
Oh, I'm so glad you saw this. Okay, what Rob found is I didn't do your book back. I want to write the symbol right. They did this, and there's all this stuff, and he found Na solid, and then there's a big fat 0 there. What is this? The F isn't for fusion. It's for, it's for formation. Do you remember when we used these numbers? And this always works. If you have a reaction, it goes from reactants to products. They all do, right? Yeah, reactants, products. But the question was, what's the delta H? One way to do it was whose law? Here's bonus points.
For what?
Whose law? And you can get the delta H for any reaction. As long as you have these tables. And every single reactant and every single product is in that table. Use this dude's law. Starts with an H. That's calculus or something, isn't it? My son was just talking about that. It's a good guess, though. Starts with an H. Hess's law. You looked up this thing for every product, added it all up. If you had 2 of them, you had to multiply this times 2. But you add it all for the products, subtract it all for the reactants, whatever you got, that was the delta H for the reaction. These are enthalpies of formation. You're missing 2 little letters. What symbol do you have to look up? I bet it's in this table somewhere. What's going to be down here? F. I don't think they put it there. I think they put it over here. F-U-S.
Yes.
That's the first time I ever struck anyone in class. Well, hard.
It's gonna be a residential punching bag.
All right, so you have to look up the enthalpy of fusion. Now, it's got to be in there somewhere.
That's what I'm hoping.
Oh,
My arm's kind of
really?
sore now. I'm having trouble turning the
Probably, I think a hint would be in the...
fusion at TF, vaporization.
That's
at T.
entropy.
Yeah.
It should be in the table. We're in chapter 2, so it should be in table 2 something. There they
Google.
are. There they are.
Standard enthalpy.
Oh, that's hydration.
Hydration.
Yeah, well, you're going to have to Google
They don't
it.
want you to do it.
You'll have to Google it, or I can tell you. This is question 10.
Garden was hoping it would say during the chapter.
2.601 kilojoules per mole. 2.601. So obviously that's stuff that is given to you on any quiz or anything. 2.601 kilojoules per mole. I must have got it from some table.
Well, it shows that symbol
Page 67. What?
They have the numbers. It's just how they write the symbols. That's it.
Oh. So the FUS is under the delta. That's how this guy does it. Mr. Atkins. You think they would all do it the same way? Okay, we have a couple minutes here.
Tip 2.3.
How would you set up 12?
11 plus.
How would you set up number 12?
There we go.
Calculate the final temperature. Final temperature of a sample of argon gas, 12 grams, expanded reversibly and adiabatically from 1 liter to 3 liters. Now again, why wouldn't the final temperature just be 273? It's this adiabatic process. Is it? Remember the story with the little container? It's got to get its energy from someplace, so it's going to go down. That temperature's going to drop. It's definitely not the same. Because it is adiabatic, the temperature has to drop. So find the relationship. Let's do what we didn't do last time. Let's look at the equation sheet. Get used to using this thing. Right? Where's our adiabatic stuff? Adiabatic and reversible. Right? And we want to know temperature. So let's throw in the one with temperature. VF.
Is it T to the power of Z?
TF. Yeah. TF to the C equals VI TI to the C. And my little c is, thank you, sir, CVM over R. Okay. Now to find this little C, this stuff, I found a table on page 923. Page 923 I found a table.
There's 2 tables. It's like Christmas.
923. Must be a bunch of heat capacities for these gases. 923. Okay. On page 923, if you don't Google this, the CVM for argon, odds are, I bet you even if you Google it, they're going to give you CPM. Because if you know one, you calculate the other using the gas constant. So all these tables, I guess that's their tradition, is to have things in the format of CPM and not CVM. So you look up what CPM is for argon and then calculate what it is for, calculate CVM. Okay. Okay. So we'll get it, plug it in. Okay. So watch your units. I bet you temperature has to be in Kelvin. Volume doesn't matter, just having the same units. And come by and ask some questions. I'll be glad to help you out. We have lab today.